everyone, and thanks for watching Edupedia World Videos. This is the third and final lecture in the topic Fluid Dynamics, and here we will cover the most important equation in the chapter called Bernoulli's equation. This equation relates the three most important quantities in streamlined flow, which are the pressure of a liquid at a particular point, the height of that point, and the velocity of the liquid at that point. The assumptions: incompressible, non-viscous, streamlined flow. In streamlined flow, we can define the velocity of a particular point as the velocity of any water molecule passing through that point at any time will be the same. This is not true for turbulent flow. The Bernoulli equation is such an important equation in this chapter that I'm going to show you the complete derivation, and it will also show you different methods on how you're supposed to solve other problems involving fluid dynamics. So let's say we have this pipe. It has different points at different heights from the ground. Also, it has a different cross-section area throughout that is not uniform. Let's assume this is the ground. We'll consider a liquid within the part A, B, C, D. Right, so this is T is equal to 0. After a small amount of time delta T, this whole liquid would have moved slightly towards the right, and it would have become something like this: A dash, B dash, C dash, and D dash. Right. We can see that the area of cross section on the left is greater than the right. That is why the length on the right is greater than that on the left, because these two volumes have to be the same. The volume of A, B, C, D is the same as the volume of A dash, B dash, C dash, and D dash. So these two areas have to have the same volume. Let's define some quantities. We are assuming these two distances to be quite small, as we are assuming the time interval to be quite small. Right. Let's say this height is h1 from the ground of this central point actually, but it doesn't really matter again because we are taking these widths to be infinitesimal. Let's say this segment is at a height h2 from the ground. Let's say the area of cross section is a1 here, and the velocity is v1. The area of cross section here is a2, and the velocity is v2. And let's say the pressure at this point is p1, and let's say the pressure at this point is p2. We are going to apply the work energy theorem on this piece of liquid ABCD. Now this particular quantity A dash, B, C, D dash, nothing has changed in this quantity except earlier the molecules which was here were now slightly displaced, but this whole system, this whole quantity of water has the exact same kinetic energy as before, has the same potential energy as before, everything is the same. So we can neglect this middle part, which is just the liquid shifted to the right by a slight amount, and we will only deal with these two parts, A dash, D dash D, and B, B dash, C dash C. For these two parts we will apply the work energy theorem. So what is the work done by the pressure? This distance will be V1 delta T, and this distance will be V2 delta T. Both of them are assumed to be very small. So the work done by this P1 will be P1A will be the force applied multiplied by the displacement. The displacement will be V1 delta T. That will be positive. The work done here will be negative because the pressure is outward, and so in the second case it will be P2A2, this is A1, V2 delta T. Right? This is the work done by the rest of the liquid on this particular parts. So this is the work done by the liquid. What is the work done by the gravity? That will be, let's call the mass of this particular quantity m for sake of simplicity. What is m? M will be A1 V1 delta T times rho, but it will also be equal to A2 V2 delta T times rho, and we already know that A1 V1 is equal to A2 V2 because of the continuity equation. So this does seem to be consistent. The work done by gravity will be mg h1 minus h2. We see that it's negative because the liquid is going upwards. We can just assume that this liquid has been transferred to this place. So the work done by gravity is negative because it is rising up. Displacement is positive, displacement is upwards, force is downwards. So work done is negative, and that is true because h2 is greater than h1. Right. So this is the net work done on this object. This will be equal to the change in kinetic energy. What is the change in kinetic energy? That will be half m v2 squared minus half m v1 squared. So this plus this is equal to this. We can write these in terms of m also. A1 v1 delta t can be written as m by rho. So p1 times m by rho minus p2 times m by rho plus mg into h1 minus h2 is equal to this. We can cancel m all throughout, and we can take rho to the other side, and the equation after simplifying which we will get will be p1 plus rho g h1 plus half rho v1 squared is equal to p2 plus rho g h2 plus half rho v2 squared. This is the essence of Bernoulli's equation, which basically says that for an incompressible non-viscous liquid in a streamlined flow, P plus rho gh plus half rho v square is a constant. So this is true at this point, this point. Now this whole quantity at this point is equal to the same quantity at this point, at this point, at this point, because there was nothing special about these 2 points. So this particular quantity is constant when a liquid is flowing through a tube in streamlined flow. This is the most important result, and we can actually see that the other results are basically can be derived from this result. For example, if the liquid is at rest, then V will be 0, P plus rho gh is constant. That basically says P1 minus P2 is equal to rho g times h2 minus h1. Right. Similarly, you can look at the other results, and you'll be able to see that all the results can be derived from this equation. That's actually not really accurate to say because this equation is derived from those equations, but as a matter of remembering or memory, if you remember this equation, you should be able to derive all other equations from this. Let's look at a couple of applications. One of them is the speed of efflux. Let's say we have liquid up to a height h and we have a hole at a small height h. There will be liquid coming out of this hole. We would like to find out the speed at which it is coming out. By the way, once you found out the speed at which it is coming out, you can add a lot of other things to make this interesting. For example, if we know the speed at which this is coming out horizontally, if we know this height, you can find out what is this displacement or after how much time it will reach the ground, or anything else which you would have needed to find out from kinematics. So this is how you can add 2 or more chapters to make even more complicated questions, and you see this in entrance examinations all the time. Right now we are just focused on this velocity. So obviously, let's say this velocity is v1, and this is the velocity with which water is coming out of this. Let's say this hole has an area of cross section a1. Obviously, if this is going towards the right, the level of water will decrease, so this line will come down with a velocity v2, and let's say this big area of cross section is a2. So we will apply the Bernoulli equation between this point and this point. So at this point the pressure will be P atmospheric, and the height is rho g capital H plus half rho v1 squared. This is equal to, at this point the pressure will be P atmospheric plus rho g small h, which is the height of this, plus half rho p2 squared. So if we know everything else other than v1, we can calculate v1 from this equation. P1 will cancel, so we get rho g h minus h is equal to half rho hang on, this should be v2, I made a mistake. Sorry. This should be v2 and this is v1. So it will give me rho g h minus h is equal to half rho v1 square minus half rho v2 square. Right? Now, in these cases, a lot of times what we can assume is A1 is much smaller than A2. That is, the tank has quite a big cross-sectional area, and compared to that, this particular hole is very small. That's a reasonable assumption, and more often than not, it will be given in the question that this area is very small. If this is true, we know A1 V1 is equal to A2 V2, so this means V1 is much greater than V2. Right, and that also makes sense. This speed at which this is coming out has to be much larger than this minute decrease in height if this area is much greater than this area. So we can often neglect V2 in front of V1, and what we get basically is V1 is equal to root of 2g h minus h, which is this particular height. This is h minus h. So we see an interesting result which was given quite early on, actually before the advent of fluid mechanics itself, by a person called Torricelli, and he basically said that the speed with which water will come out through a small hole will be the same speed with which an object would fall if it were left at this height. We know that if we drop an object from this height, at this point its speed will be root 2g h minus h. So he said that the speed of water coming out of hole will be exactly the same speed, though I don't think he actually found out the formula for this, because Bernoulli's theorem and everything came afterwards. But based on experimental results, he gave a hypothesis that this particular height, and if this area is very small, then the speed of water coming out here would be the same as that of an object if it was dropped from this topmost point. Right. There is one more thing remaining, and that is a Venturi tube. Sorry. And a Venturi tube is used to find out the speed of water flowing through a particular area. So the construction of the Venturi tube is like this. You take the water whose speed you need to measure it, and you pass it through a cross section like this. Here. So you pass it through a constriction. This area is A1, this small area is A2. So we'll see that the liquid will end up rising in these two paths. The liquid will come up to a height here, and it will come up to a height here, and let's call the difference between these two heights h, and let's say this is going in with the speed v1 and this is coming out with the speed v2. And the first equation we know from the equation of continuity will be a1 v1 is equal to a2 v2. Secondly, the difference between pressure at these 2 points, because these 2 points are exactly at the same height, will be equal to the difference between kinetic energies by Bernoulli's theorem. So the second equation will be rho g h is equal to half rho v2 square minus half rho v1 square. So we can measure h easily. A1 and A2 we already know. So these are two equations, and we have two variables, v1 and v2. So we can calculate both of them. So if you want to find out the the important quantity was v1. So we have liquid flowing through a particular tube. We can put a Venturi tube of the same area of cross section next to it, and we can measure the difference in heights, and if we know the areas of cross section, that will give us the speed through with which the liquid is flowing through this tube. So this completes fluid dynamics. Thank you.